Good day to you all. Today in this session we are going to talk about and continue on the design of absorbers that we had started in the last session. What we start with is a little bit of recapitulation on the absorption and solvent regeneration. We know that they have to occur in pairs, particularly in cases of continuous plants, where solvent circulation is also an important thing, and total cost or the economics depends on the combined arrangement of absorption in the absorber, in the solvent, and the regeneration of the solvent circulating between these two units. Wherever we are posed with a problem, this also we have discussed that we start with a conceptual design phase. So, in case of absorption, the first question comes, what is the composition and the flow rate of the feed gas? This also we have discussed in the last class. We need to know the capacity, which is basically the scale of operation, whether it is going to be one time or it is going to be a continuous matter for quite some time. We need to have a target of removal of the component for the gas phase. The choice of solvent is absolutely important, because it is the solubility of the solute in the solvent governs the process. But when you choose the solvent, there is not only the consideration for the absorber, but for the solvent regeneration also. The regeneration often is by boiling the solute off. So, that consumes a good amount of energy. It could be by stripping with an inert gas as well, or a reboiled stripper. It could also happen that a small distillation column will be used. Most of it will be the stripping section. We definitely in our simplified treatment will be considering that it is only the solute component which is transferred from the gas to the liquid phase. But however, in reality, some small amount of some component or all components of the solvent may also get transferred from the liquid to the gas phase itself. A common thing being, when the gas is unsaturated with respect to the solvent liquid, some amount of vapor phase transfer or vaporization of the solvent and joining the gas phase will definitely be happening. It is important to note one thing, that is the absorber operating temperature. Normally, absorption process is associated with liberation of a small heat of absorption. So, what we have here based on the fundamental thermodynamics, that absorbers work better at lower temperatures. So, quite often you will find the solvent before entering the absorber is from a cooler. The pressure plays a key role in the solubility of the gas in a liquid. So, quite naturally, higher the pressure, more will be the carrying capacity of the solvent with respect to the solute. And if we are talking about the pressure, we have to talk about the pressure drop in the equipment, and definitely the supply pressure of your gas should be sufficient enough, so that the affordable pressure drop can be availed from the source. If it is not possible, then definitely the pressure has to be boosted by either a blower or a compressor, as the case can be. In the design, we have to decide on the option of the contacting device. In reality, most of the absorbers, they use either a packed bed or a stage wise plate tower. Most of the time, the number of ideal stages required for this contacting is low, typically maybe around 3 or so, it could be even 4. It is not large. So, absorbers quite often will be using low efficiency trays like the sieve tray, because we can always provide quite a bit of extra number of trays to account for its inefficiency. Typical efficiency of a sieve tray will be of the order of maybe some 40% or so, it could be slightly less than that even. During the conceptual design phase, we need to have a process scheme, and the process scheme should include not only the absorber, but the solvent regeneration system also. And at the end, we reiterate by saying that the economics of the entire system depends on the combined arrangement of the absorber solvent regenerator. With this, what we do is we talk about an example absorption system. See, the fuel gas very often produced in the refinery, which is a hydrocarbon mixture in fact, it contains plenty of things. It contains H2S, carbon dioxide, hydrogen, small amount, methane, ethane, some amount of C3, C4 and C5 hydrocarbons. It is typically called sour due to the presence of H2S. The available temperature is around 40 degrees centigrade. It is around 40 degrees centigrade. Now, this H2S and carbon dioxide has to be removed. In fact, what is done in a refinery is to remove these gases, and the H2S is sent for recovery as sulfur from H2S. So, this is a very important unit, not only to remove H2S and CO2, but also for providing the raw material which will be used for production of sulfur. Typically, the H2S and CO2 they are not highly soluble in water or in aqueous phase. But if you have roughly some alkanolamine solution, in this specific case we are talking about diethanolamine or DEA, 10% aqueous solution, 10% aqueous solution as a solvent. So, the solvent consists of two things. It contains of water and it contains 10% by weight of diethanolamine. Now, this together they have high affinity for H2S and carbon dioxide. So, naturally when these two come, when the liquid and the gas come in contact, the solvent and the gas feed, the H2S and CO2 get transferred from the gas to the liquid phase, leaving the hydrocarbons and the hydrogen, and if there be a small quantity of nitrogen which is also there, which is not mentioned here, but it may also be there in some cases, leaving in the unabsorbed phase. The solvent regeneration of the solvent which is rich in H2S and CO2 is rather easy. If you boil it off, the solubility decreases, and this is done in a reboiled tray column, typically with around 24 trays, and you have a feed tray which is number 5 from the top. The top product is a gas, primarily H2S, carbon dioxide and H2O, H2S, carbon dioxide and H2O. You will notice one thing, it will also contain a small quantity of DEA, and there is a special configuration which is done in order to reduce this particular loss, that we will see after this. You will notice in the scheme that is presented immediately after this that there is a cooler for lean amine. It brings down the absorber entry temperature to around 40 degrees centigrade, which is very close to the gas supply temperature. In fact, during absorption, the amine temperature rises slightly, possibly to around 45 degrees centigrade or so. Now, in order to regenerate the rich amine, or rather the amine solution which is rich in H2S and CO2, it is sent to the next distillation column after preheating it. We will see there is an arrangement of preheating this particular stream with the column bottom itself. We also have noticed that along with the gas, some amount of H2O will be leaving, and we have also mentioned that apart from H2O, you will also have a small quantity of DEA loss from this phase as well. So, what happens actually is there has to be a makeup stream of DEA as well as water, which can be either on a continuous basis or periodic. Typically in refinery you will find that there will be such makeup once a week. So, this is in brief, we have an idea of a practical H2S removal system from the fuel gas. You will also note here that the choice of the solvent diethanolamine here is for a very specific purpose. It is the weak chemical bond it forms with H2S and carbon dioxide, which increases the liquid phase of the solvent capacity to absorb much higher. That means the effective solubility if I use only water and the effective solubility that I get if I use 10% diethanol solution, the DEA solution will have many times higher capacity to absorb. That means the grams per meter cube of the solution which is getting circulated would go up substantially. So, this would definitely require less amount of circulation. So, you must choose a solvent which has got high capacity, and you have chosen a solvent in order to have the high capacity which forms a weak bond. Now, the question is why weak bond? If I have something, a solvent which forms a very strong bond with the solute, it becomes very difficult for it to break this bond and release and regenerate the solvent. So, in this specific case, DA is found to be quite suitable. In fact, there are quite a few other alkanolamines like monoethanolamine and MDEA, which are also used for removal of H2S as well as CO2. This is a very standard absorption regeneration process. Now, what we do is let us look at a practical implementation of this arrangement. This is the scheme. What you have here is a sour gas feed. It is sour because of the presence of H2S, and it contains these components. It has got carbon dioxide, it has got hydrocarbon, it has got small quantity of nitrogen and hydrogen as well. Here you have a packed tower which is being used as the absorber. Now, once this H2S is removed, it is no more sour. So, the exit is the sweet gas. In fact, the sweet gas will be containing very small quantity of residual H2S and carbon dioxide, and the rest amount will be the unadsorbed material which is hydrocarbon, nitrogen and hydrogen. I was telling that this is available at a temperature close to 40 degrees centigrade, and the solvent which has got minimum quantity of H2S and CO2 after regeneration in this particular section. This section is a regeneration section, has got very small quantity of CO2 and H2S. So, that is what is coming here to the top of the tower for absorption. Now, this is cooled in a cooler to get to a temperature of close to 40 degrees centigrade itself. Often this temperature will be close to around 45 degrees centigrade. These are typical operating values for this type of towers. I iterate once more that we say the solvent is lean in the solute, and this solvent after absorption becomes rich in the solute. So, basically this is the rich solvent, this is the lean solvent, and the solvent keeps on circulating between these two units. Now, let us look at the process which we have grossly described in the previous slide, and we have talked about it, is here the regenerator. In this regenerator, as it looks like, what you have here is a reboiled column. It is a reboiled column. What we have mentioned, there are 24 trays. The feed is on number 5, the overhead reflux is on number 1. So, the bottom tray is number 24. You will see here that below the feed we have a large number of trays, that is from 5 to 24, these are the stripping trays. So, you have a good amount of stripping done. That means, as the rich amine falls down through these trays, the vapor which is generated here by the reboil strips out the H2S and CO2, and it finally goes out. Possibly you have a query now that why is the feed on number 5 and not just like an ideal stripper, it is on number 1, that is not on the top tray. Here it is something which is very important with respect to the engineering of this type of columns. One thing you will find that this is a column in which there is only a vapor draw off. It is a vapor phase which is drawn off as the top product. The accumulator, the vapor comes here, it goes to the condenser, it condenses, comes to the accumulator. The entire liquid is refluxed back to the top tray. So, this is in industrial parlance, but it is not exactly the way the textbook says. This is called a total reflux column operation, but in fact that is also a misnomer in the textbook terms. But what is meant here is the top product is only a vapor. So, what you have in the top is a partial condenser. Now, what you have in addition is the question to be still answered is why is the feed on number 5? The purpose that we have the top product, ideally the top product would have been the H2S and CO2 only, but what is refluxed here is primarily H2O. I could have given the feed on the top tray itself, but in that case some amount of DA would have gone to the top also. It would have vaporized and would have gone to the top. That is the reason you have the feed on the 5th tray and not on the top, primarily to reduce the loss of DEA. So, with this configuration you have only a small quantity of DEA which is lost as the overhead vapor. Now, it is a reboiler column. Typically, it will be heated with hot oil. Possibly some hot oil stream which requires cooling within the refinery will be used as a source of heat in the reboiler itself. Here what you find is another thing which is also which you have learnt in case of your distillation column also, that you need to preheat your feed. That means your distillation here requires energy to be supplied, and one source of energy is your reboiler. The other source of energy is basically your preheating heat exchanger. In your distillation column here, the bottom temperature is higher than the feed temperature. Quite naturally, there can be some amount of heat that can be transferred from the bottom stream here to the column feed, and which is definitely done in this particular heat saving scheme. Basically, it is a heat conservation scheme. Anyway, still you will not be reaching 40 degree centigrade, because at the bottom the temperature will be around 115 120 degree centigrade, but it cannot just come down to around 40 degrees. So, you usually will be having a cooling water heat exchanger which will be cooling down the temperature to around 40 degrees centigrade. So, what you do now is we have an idea that how an absorber regenerator system works in industry. We have a typical industrial example, and we now move to the actual designing. We look at the steps of designing of the contactor. We already have said that right at the beginning of the course that we are going to have an equilibrium based approach. That means, what we intend to do is to find out the number of ideal stages, which means that the vapor and the liquid streams leaving will be at equilibrium. We find out the number of such stages, which is the number of ideal stages, then we implement it. So, what we have is two steps. The first is estimation of the number of ideal vapor liquid contacting stages required for the separation. After all, it is a separation equipment and a separation process. Then what we do is we evaluate the equipment options and select, and then after we go for the detailed design of this. Before we move further, there is something which I want you to note here at this particular moment of time. That is, we are going to use a specific convention here. We are going to say that your L and G, these are going to be the total molar flow rates, the moles per hour of total number of moles flowing in a stream. Similarly, the corresponding number of moles present in that stream except the solute are denoted by L dash and G dash. I have a question here. When will the L dash and G dash remain the same across the column? That means, if I have my column here, if I have the gas entering here, my liquid entering here, and the liquid coming out from here, and my gas going out from here, in that case, if I take any section, I have a stream of gas G dash going up and I have a stream of L dash which is coming down. Now, my question to you right now is, under which condition or which assumption G dash here and the G dash here is same, and if it is same here and here, your L dash here and L dash at this particular point will also have to be the same. So, what you do now is basically have an idea that when can this happen? What is G dash? G dash is the number of moles in that particular gaseous phase which is moving up except the solute component. So, quite naturally, if any of these components do not get transferred to the liquid phase, my G dash will be the same at this location and this location also. So, that is the condition, and the same thing is true in case of L dash also. If no component of the liquid gets transferred, I mean except the solute, there is no component of L which gets transferred to the gas phase during its travel from the top to the bottom of my column. In that case, my L dash will also remain constant. We define the compositions now. The conventional composition we have been using for mass transfer are the mole fraction, X denoting the liquid phase mole fraction and Y denoting the vapor phase mole fraction. The mole ratio capital X and capital Y basically means, it is defined here very explicitly, X or Y means moles of solute in the stream divided by the total moles. Capital X or capital Y means moles of solute in the stream, it is the same, divided by the moles in the stream excluding the solute moles. So, quite naturally, just by the solute balance you can say capital X equals small x divided by 1 minus x, and similarly capital Y will be small y divided by 1 minus y. It can also be said in that particular case that L into x, what does it give? L into x gives basically the moles of solute in my stream, and L dash into capital X will also be giving you the same. So, naturally this is an equality, this is an equality. We are going to use these equalities after this when we frame up the design equations. We come to the state of designing now. The number of ideal stages of contacting required is basically the purpose of the design step. We have simply written here, we have drawn here the column itself, where I have the top stage is number 1, the bottom stage is capital N, number n. Any general stage is small n, and what the convention that we follow is, if it is coming from a particular tray number n, if the liquid falling from this will be Ln, and Gn will be definitely be telling us the gas which is leaving this particular stream. So, quite naturally, if n is this particular ideal stage and I have one more stage below which is going to be number n plus 1, this liquid stream is going to be Ln, its composition Xn, and similarly, since the vapor here is going to come from here, in fact it is Gn, there is a typing error here, Yn plus 1, and it is going to be Gn plus 1 here. So, what I do here is basically I have an external liquid which is coming from the top, which is basically my solvent, and it's having a it's say this one is number 1. So, the one ideally, if it exists at all, we have denoted this particular stream with a subscript of 0, and its flow rate is L0 and its composition is X0. Exactly in the similar way, since the top stage is 1, the gas leaving is having a flow rate of G1 and the corresponding composition is Y1. What we do now is we simply draw a control volume. We draw a control volume and try to do a solute balance here. What we find here is, if I say my L dash is a solute free flow rate, in that case my L dash, when it falls from particular external point to a particular point Ln, the composition corresponding to Xn will be capital Xn. So, the enrichment, or rather it is not the enrichment basically. So, the change in composition from here to here is going to be this, and in case of gas it is going to be this. Here Xn will be higher than X0 because it picks up the solute. Similarly, Yn plus 1 is also higher than Y1 because it is more close to the entry where the concentration of the solute in the gas phase is higher. Similarly, exactly the same thing I could have also written in terms of L, G, small x and small y also. In fact, in case of absorption, both the conventions and the units are used. I just rearrange my upper equation here, and this becomes this particular expression. This has a very interesting point here right now. It shows the relationship between Xn and the relationship and the corresponding vapor. That means, if I am talking about the column at any particular point, it's relating the liquid composition with the vapor composition in this thin section. That means, Yn plus 1 is the vapor approaching the nth section, nth ideal stage, and Xn is basically the composition of the liquid leaving that particular stage and falling down. And this is a generalized relationship. So, this definitely will be valid all through. So, I could also remove this y and x, and I could write here this as a generalized expression also. So, what we do now is I move forward and we look at the data which is available with me. I can have the equilibrium data at the average operating condition of the column with in terms of either small x and y or in terms of the capital X and y. We know what is the interchangeable formula. If I have small x, small y, I could convert it to capital X, capital Y, or I could do the other way also. If one is available, the other is also known. So far what we have understood is we are going to use two definitions of the flow rate. One is including the solute, which includes a dash, that means L dash typically, or G dash, which means it is solute free, and otherwise it is either L or G, which is basically the total moles per hour flow rate. So, what we do right now is we have a look at the design graphical procedure. What we have here is the gas coming in. This one is a nth tray and this one is the top one. So, naturally Gn plus 1 comes in and G1 goes out as per our convention of leaving and entering a particular ideal stage. Similarly, L0 is the external solvent inflow with a corresponding composition of X0, and the whatever comes out after picking up the solute is Ln and Xn correspondingly. What we do now is basically we take a control volume and we make a solute balance. If we make a solute balance here, what we find is the solute entering from this is basically L, it is basically G dash. The G dash remains all through same because without the solute, and if we assume there is no liquid composition, no liquid component going to the gas phase, your G dash will be all through same. That means the moles of solute free gas which goes up the column is same in every stage. So naturally G dash multiplied by whatever is a corresponding composition is basically capital Y. We know here the capital Y denotes the solute free composition in n plus 1 minus capital Y 1 is the amount of solute transfer in this particular section. And where does it go? It goes to L dash, which is basically the liquid which falls, and it gets enriched up to Yn, and the enrichment starts from the composition of Y0. So this is the balance. This we can say that this is what is relating to, sorry, this is x, this is also x. I write this once more, it is G dash into capital Y n plus 1 minus Y1 equals L dash x n minus x0. So we could take this. This is the equation which relates xn and yn plus 1, which are the composition of the two components, the gas and the liquid phases, here and here. And we know also that my G dash and L dash is same all through. In your design problem, what are the things known? My L0 will be known, my X0 will be known, my gas inflow rate will be known, my gas composition will be known, the desired gas composition at the outlet will also be known. So here if you see, if you somehow know G dash and L dash, the relationship between Yn plus 1 and Xn is fixed. We know the relationship between the capital Y and small y and the small capital X and small x. So quite naturally, we also have an equivalent relationship between the small x and small y in a general sense as well. So what you have here is that basically the equation of the operating line, which is also shown here in the generalized form. Now there is one more thing that we have to keep in mind. This is for a particular value of your L operating, and here we are using a parameter L dash operating by L dash minimum, which is equal to P, which is also a design input. So in order to have this, we need to find what exactly is the L dash minimum. L dash minimum is the minimum flow of solvent required in order to remove this much quantity of solute. When can this happen? This can happen only when my Xn here is basically a equilibrium composition corresponding to the value Yn plus 1. So if I have my XY diagram here, on which this is my equilibrium line that we have already marked here as the equilibrium line, and we have marked here the Yn plus 1 point, and the corresponding point of Xn dash is going to be this. Now we have this with me. In this G dash is same. My L dash this time is L dash min, and here all parameters are known, and this Xn is basically Xn dash. So it's possible for us to find out the only unknown parameter in this particular equation utilizing the same equation or the solute balance, which is basically L dash min. And if you have decided typically on a P value which is about 1.5, we are going to operate L operating or L dash operating is equal to 1 P into L dash mean, or about 1.5 times L by mean. And corresponding equation we have here, which is also possible to plot here. You will notice one thing, that this operating line equation is above the equilibrium line equation in case of the absorption phenomena, and in case of stripping it will be below this. The procedure is exactly the same. With this, I think I will stop here, and will illustrate the details of the procedure with a numerical example in the next class. The steps are written here very clearly. The operating line equation is also here in a generalized form using that particular P. It could also be written in terms of capital X, capital Y if you are going to use the coordinates capital X and capital Y also. And the steps are very simple: draw the equilibrium line, locate the solvent entry point on the operating line, which is the x0, y1, the bottom left graph point that we have started with. Locate the minimum feasible solvent rate on the equilibrium line, which is that xn star. We find out xn star. Based on that, we calculate and find out what exactly is the L min. Then evaluate based on the value we have for P, what exactly is going to be my L operating, and based on the P value we have adapted, we find out the equation of the operating line for L operating. Now, here you will also notice something. If you are using a small x small y coordinate, your operating line will also be non-linear. The generalized formula expression is given over here, and basically it is to be drawn covering the entire range of interest for x and y. Now, the procedure is simple, and we have found out that with 3 stages, which is noted to be the number of ideal stages required for this problem, which is m, or number 3 in this particular case. And the next stage is basically a situation, a very special case when your solute concentrations are really low. In that case, it is possible for you to derive an analytical expression where, based on the linearity of your operating line as well as the equilibrium line, which will give you directly the number of theoretical stages as n given by this expression, which involves a slope of the operating line, which is basically delta x by delta y, that is the equilibrium line slope, and the subscript represent the ends. In case an average value is to be used, typically it is the square root of m1 into m2, which is used as the m value. This is valid over a dilute range only. The equilibrium line is nearly linear when I have m1 and m2 same. Next comes the realization of the number of ideal stages in practice. We take care of the inefficiency of the real life by considering an equilibrium, by non-equilibrium, that means a factor of an efficiency, and we carry this on in the next class for finding out the details.